Hello students, in this chapter you will study the consequence of Lorentz transformation equations used by Einstein in the special theory of relativity. In this chapter we will study the two consequences. One is what is called as contraction of the length. It is called the length contraction, which means if you measure the length of a body at rest, and if you measure the length of the body when it is moving in the direction of its motion, then length of the body at rest is more than length of the body when it is moving. That is, when the body moves, there is a decrease in the length of the rod and what is called as a length contraction. Another consequence we'll see is what is called as a dilation of time. Time dilation. Dilates means to become a bigger. Time dilation means the time interval become longer. Time interval becoming longer means time becoming slower. That is, if one finds the time on the clock which is at rest and time of the clock when it is moving, then time interval showed by the clock which is moving is longer than time interval shown by the clock when it is at rest. That is called as a time dilation or slowing down of the time. In next chapter, we study also one more consequence, that is about the increase in the mass when the body is moving. So when the body is at rest, it has one mass, and when it starts moving, and if one observes it, then mass of that body is found to be larger. So there is an increase in the mass. So these three consequences of according to the special theory of the relativity we'll study in this section on the relativity, but there are also more consequences which are not part of our curriculum. So first let us consider what is called as a length contraction. Now what we do here is we take the two inertial frame, the frame S and frame S dash. The frame S dash is moving along the x-axis with velocity v as observed in the frame S. We keep a rod in the second frame. Example, this is the first frame is the road on the earth and observer is there standing on the road, and the second frame S dash is the floor of the bus and you are keeping the rod on the floor of the bus. So when the bus moves, the rod in the bus is stationary, but it moves along with the bus. So observer in the frame S, that means observer on the road, will see that the rod is also moving. Now here we have shown the x coordinate of the rod with respect to the frame S dash. It is x1 dash and x2 dash. So as measured in the second frame, the length is x2 minus x1 dash, x2 dash minus x1 dash. That means, see, observe in the second frame, you will see that the rod is at rest. Although the frame is moving, the rod is at rest. Just like when the bus is moving, the rod which is kept on the floor of the bus is at the rest. So you will see, if we measure the length, you will find it is x2 dash minus x1 dash. Now here we use a Lorentz transformation equations. These are the Lorentz transformation equations we write it for x1 dash and x2 dash. So x1 dash equal to x1 minus vt1 root of 1 minus v square by c square. x2 dash equal to x2 minus vt2 divided by root of 1 minus v square by uh, c square. So this x1 is the position of the one of the end seen by the observer in the frame S, and x2 is the position of the other end of the rod seen by observer in the first frame. And this t1 and t2 are a time at which that positions are measured. Then you will find the difference between those two, x2 dash minus x1 dash. You get it like this. And when you simplify this, what you get is x2 minus x1 divided by root of 1 minus v square by c square minus v t2 minus t1 root of 1 minus v square by c square. Now we have found this x2 dash minus x1 dash, the length of the rod measured in the second frame, and how it is related with the length of the rod x2 minus x1, that is which is measured from the first frame, and a second term is there connect t1 and t2. But let us say that the both the position are measured at the same time. So simultaneously you find the position of x1 and x2. So that means a time t1 is equal to t2. So t2 minus t1 is 0. And what you get is x2 dash minus x1 dash equal to x2 minus x1 divided by root of 1 minus v square by c square. Now, the length of the rod as measured in c is x2 minus x1. So it is equal to x2 dash minus x1 dash root of 1 minus v square by c square. Now, instead of writing x2 minus x1, that is the length of the rod as measured in the first frame, we write delta x. So delta x is the length of the rod measured with respect to the first frame, and x2 dash minus x1 dash is the length of the rod measured in the second frame. Now we write delta x suffix 0 because in the second frame the rod is at rest. In the first frame it is moving. Then this root of 1 minus v square by c square is very less than 1, because we know that the velocity of the light c is 3 into 10 raised to 8 meter per second, and normally the bodies can move, example rod can move as compared to the velocity at a much lower speed. So v is much lesser than c, so v square is much lesser than c square. That means v square by c square is very small as compared to 1. It can very much less than 1. And what happens is root of 1 minus v square will be less than 1. See 1 and v square by c square is less than 1. So root of 1 minus v square by c square is much less than 1. So that means this x2 minus x1 is less than x2 dash minus x1. So delta x is less than delta x 0. That means, see, delta x is the length when it is when we measure the length of the rod when it is moving. Delta x 0 is the length of the rod when it is at rest. So when you measure the length of the rod when it is moving, the length is smaller than the length of the rod when it is at rest. So this is called as a length contraction, because length appears to be less. Now this, when it is at rest, that length is called the proper length, because normally in our day-to-day life we do the measurement when object is at rest. So we call it the proper length, or length when it is at rest, or length in what is called the laboratory frame. See, in laboratory what happens, we take a device, it is at a rest. So it is also called a length in the laboratory frame, means length measured when it is at rest. It is also called the true length. So these are different words used. And delta x is a length when it is moving, and when it is moving, so it is less than the actual length. So we call it as the improper length. So these two words are used. But here what happens is, see, when the rod is moving along the length will get contracted and not the breadth. Okay, suppose a rectangular body starts moving with a certain velocity, so the side which is in the direction of motion, that will get contracted, and not the side which is perpendicular to the motion. Okay, but suppose it is moving in a plane, that means x as well as y direction, then both the dimensions will get contracted. So this you should keep in mind. So there are problems based on this. It is given in your notes, and they are very simple. And with the direct substitution you can get. But remember, you should know what the delta x suffix 0 represent. So that is when the rod is at rest, and delta x is when the body is moving. Remember that length which is moving in the direction, that length gets contracted. Now I'll mention about some examples where the length contraction takes place. Now in the nature there are what are called as the elementary particles. Elementary particle means particles which cannot be divided further. Example, electron you cannot divide into two parts, or a proton cannot be divided into two parts according to present theory. Okay, then a neutron cannot be divided into two parts. They are called the elementary particle. So like that, there are many more elementary particles. In fact, our Earth is showered with a large number of different elementary particles from the outer space. In fact, there are something called as cosmic rays. Now these are the these a shower of the elementary particle coming from the outer space, and they enter the Earth's atmosphere, and they are made of they are recognized by different names. There are many types, and because of their small size, they move with the high speed, and the because they move with very high speed, very close to the velocity of the light. What happens is the length distance covered by it. Distance covered by it means given particle is with respect to itself it is at rest, but for observer it is moving. So for observer who is looking at that elementary particle which is moving with very high speed at a uh, at a given interval, the distance covered by it is measured to be smaller than actual distance carried by the elementary particle, and this is experimentally observed. Even the spaceship, so these aircraft which are sent in the outer space, maybe on the moon or Mars or some uh, other planets or other galaxies. Now they move with very high speed, and when they found from the Earth, when they observed this measurement, they tried to measure the length of that spacecraft. Then it is found that length uh, from the uh, uh, observer by the length observed by the observer on the Earth is smaller than the actual length when it was measured when it was there on the Earth at the rest. So these are the examples I'm giving you. Next, let us take the example of a dilation of time, slowing down of the time. Now let us consider two different events taking place in S dash. See, two different events. So something is happening at one point in the frame S dash. Another event is taking place in the same frame. Then we keep the clock in the second frame as well as the first frame. And from the first frame, we observe the time interval on the clock kept in the first frame and the clock kept in the second frame. Okay, so now we do the observation from the first frame for both the clock. So now here, because of that, we have to use the inverse Lorentz transformation equation. So some two different events, phenomena are taking place in the second frame, and there is a clock is kept in the second frame, and one more clock is kept in the first frame, and we observe the time interval between these events in on the both the clock. So now we make use of inverse Lorentz transformation equation. This is there, t1 equal to t1 dash plus x1 dash v by c square, root of 1 minus v square by c square, t2 equal to t2 dash plus x2 dash v by c square divided by root of 1 minus v square by c square, and this we have proved. Now find the time interval t2 minus t1. Now when you find difference between these two equations, you get like this, and when you simplify, you get t2 dash minus t1 dash root of 1 minus v square by c square minus v by c square x2 dash minus x1 dash divided by root of 1 minus v square by c square. Now next slide will say that both the events which have taken place happens at the same position. So x1 dash equal to x2 dash. Okay. So now here x2 dash equal to x1 dash. So this second term becomes equal to 0. x2 dash minus x1 dash is equal to 0, and you get this t2 minus t1, t2 dash minus t1 dash divided square root of 1 minus v square by c square. So this interval as measured in the first frame is delta t, and this interval as measured in the second frame is delta t 0 divided by root of 1 minus v square by c square. As I said earlier, this delta t is a time interval when it is at rest. It is called as a proper time, and delta t is also called the improper time. Or delta t suffix 0 is called as time measured in the laboratory frame, and delta t is a time measured when it is moving. And this as I mentioned earlier, this this v square by c square is less than 1, so this quantity is less than 1 minus some quantity, so it will be less than 1. And since this is a less than 1, so this is a less than 1, that means this t2 minus t1 is greater than t2 dash minus t1 dash. That is, delta t is greater than delta t 0. That means the clock in S records time interval more than that in S dash. The clock, that is, there is a slowing down of the clock, dilation of the time. That means clock runs faster when at rest relative to observer. Its rate slows down when moving. Now this dilation of the time phenomena is also proved experimentally. So we know that a radioactivity sample, there is something called as a half-life. Half-life. If half-life is more, um, then the decay of that element is slower. Longer time it will take to decay. So if the half-life is more, then it will take longer time for that material to decay into another element. Now what they did was a given radioactive sample like a thorium, let us say you take a thorium, find its half-life. That means find its half-life means in laboratory frame means it is at rest. Then it was kept on the rotating disk, and the disk was rotated at very high speed, and then they found its decay rate. Its half-life was found. The half-life of this, when it was rotating very fast, that means when it was moving, it is moved very close to the velocity of the light, so it is moved with very high speed. So half-life of the radioactive sample, which was found to be moving with a very high speed, was found to be longer than the half-life of the radioactive sample which was at rest. So that means when it moves at a high speed, the decay slows down. Half-life is longer means what? It takes more time to decay. Okay. Now, next example which I have given, uh, no one has experienced this, but with the Einstein's calculation, they found that suppose there are a group of friends on the earth, age of 15 or any other age, same age. Then one of them goes in a spaceship which is traveling with the speed of light, very, very large speed of light, 3 into 10 to 8 meter per second. And he does this for 5 years. Then he arrives back on the earth. He arrives back on the earth. Then after 15 years, when he was 15 years old, he has gone in the spaceship which was moving at a very high speed, and he spent uh, 5 years in traveling. And when he comes back, he is a 20 years old. But all his friends were there on the earth, so at a relative rest, they become 65 years old. 65 years old. Okay, so that means, say, his friends were there on the earth, their time has run very fast. Whereas since he was moving with very high speed, the time has slowed down. So when he comes back, he is only 20 years old, whereas the other friends have become 65 years old. Okay, so this is the phenomena, but no one has experienced this so far. But especially in the Indian mythology, there are many stories. Okay, there are tales like, okay, and there are stories where someone went in the traveling in the cosmos with a high speed. So from the earth, he simply just disappeared. Disappeared means what? He went with a very high speed, and when he came back on the earth, especially there's the story of the one king. Uh, Someone took him for the tour, cosmic tour, with very high speed, and when he came back, he found that he's very young, but his great grandson was ruling the kingdom. Okay, such this type of the concept was conceived by ancient civilization. Not only in India, in other countries also, there are such stories. Okay, so they are related with the theory of the relativity.